Crankshafts are one of the most vital components in internal combustion engines. They convert the reciprocating motion of pistons into rotational motion, providing power to drive the vehicle or machinery. Given the mechanical demands placed on them, crankshafts must exhibit extraordinary strength, durability, and precision. The manufacturing process of crankshafts is complex, involving multiple stages, each crucial for ensuring the final product meets stringent performance standards. The process begins with selecting the right material. The billet, or raw piece of steel, is heated to a temperature between 1065 degrees Celsius to 1230 degrees Celsius, a critical range that allows the steel to become malleable without causing it to crack. Once the billet reaches the optimal temperature, it is moved to a forging area where the steel undergoes initial shaping. Using either a mechanical hammer or a hydraulic press, the steel billet is subjected to extreme force to shape it into a rough outline of a crankshaft. This stage involves elongating and compressing the material, establishing the basic form that includes features like the crank pins and the counterweights. The forging process ensures that the steel grain structure is aligned for optimal strength in the final product. Next, the pre-formed billet is placed into specialized molds. Using a hydraulic press, immense pressure, ranging from 3,500 to 10,000 tons, is applied to the billet to refine its shape. After the initial forging, the crankshaft is still hot and must undergo heat treatment to increase its hardness and wear resistance. This is typically achieved through a process called quenching, where the hot crankshaft is submerged in oil or water to rapidly cool it. This cooling process helps harden the steel's surface while maintaining the internal material's toughness. Some crankshafts may also undergo additional heat treatments such as tempering or annealing to relieve internal stresses and enhance ductility, further improving the component's overall performance. Once the crankshaft has undergone the necessary heat treatments, it is ready for rough machining. This stage involves the use of CNC, computer numerical control, machines to remove excess material from the crankshaft's surface. Precision tools such as turning and milling machines are employed to begin shaping the crankshaft's critical features, including the main bearings and crankpins. During this phase, oil passages are also drilled to ensure proper lubrication once the crankshaft is operational. After rough machining, the crankshaft is subjected to fine machining. In this stage, highly precise equipment such as grinding machines are used to achieve a smooth, polished surface with minimal tolerances. This ensures the crankshaft maintains exact dimensions necessary for its function, often within micrometric precision. At this stage, the crankshaft is also treated to enhance its surface characteristics. The final step in crankshaft manufacturing is quality control and dynamic balancing. Every crankshaft undergoes rigorous inspections to ensure that it meets all dimensional and performance standards. This includes checking the accuracy of dimensions, surface finish, and overall structural integrity. Additionally, the crankshaft is dynamically balanced to ensure that it will operate smoothly without excessive vibrations when placed under load. Throughout this process, precision is paramount. Even minor deviations during any of these stages can lead to a significant reduction in the performance and longevity of the crankshaft. The combination of advanced materials, cutting-edge machinery, and stringent quality control makes crankshaft manufacturing a highly specialized field within mechanical engineering. The resulting product must endure extreme conditions, from high speeds to heavy loads, and play a pivotal role in the smooth operation of an engine. Von Schoen GmbH is renowned for its high-precision crankshaft manufacturing process, which is designed to produce high-quality, durable components for the automotive and industrial sectors. The process begins with open die forging, a fundamental step in shaping the raw material into a rough crankshaft form. During this stage, the raw material, typically high-grade steel, is heated to high temperatures and subjected to immense pressure through a forging press. The steel becomes malleable, allowing the use of large hammers or presses to shape it into the basic geometry of the crankshaft. This forging process helps align the grain structure of the material, providing the crankshaft with enhanced mechanical properties such as strength and resistance to fatigue. Once the rough form has been created, the crankshaft is cut to length using precision cutting tools. This process helps remove any excess material from the forging stage, ensuring that the component is closer to its final dimensions. The next step in the manufacturing process is quenching, which involves heating the crankshaft to a specific temperature, typically between 800 degrees Celsius and 900 degrees Celsius, and then rapidly cooling it by immersion in oil, water, or a similar medium. This heat treatment process hardens the material, making it more resistant to wear and improving its strength. The cooling rate is carefully controlled to ensure the crankshaft does not develop undesirable stresses or cracks, which could affect its performance during operation. After passing the initial testing, the crankshaft undergoes rough turning, a process where the component is shaped to its approximate final dimensions using a CNC lathe. This step removes the bulk of the excess material from the crankshaft, refining its overall shape and preparing it for more precise machining. Rough turning also ensures that the crankshaft is structurally balanced and ready for further finishing operations. The next step, pre- and finish turning, involves refining the shape and dimensions of the crankshaft even further. In this stage, the crankshaft is rotated in the lathe while tools are used to finely cut the material to meet specific tolerances. This step ensures that the crankshaft's overall dimensions, such as the main journals and counterweights, are accurate. It also eliminates any remaining imperfections left from the rough turning process, giving the crankshaft a smoother surface and better dimensional precision. Following the pre- and finish turning, fine turning and grinding are performed to achieve the final, precise dimensions of the crankshaft. The fine turning process further refines the crankshaft, reducing the variation in diameter and ensuring it meets the specified tolerances. The grinding process follows, using high-precision grinding machines to smooth the surface of the crankshaft, ensuring a flawless finish. This stage is critical for ensuring the crankshaft's smooth rotation in the engine, which is crucial for maintaining engine performance and longevity. At this stage, drilling is performed to create lubrication channels or other necessary features in the crankshaft. These holes are essential for the distribution of oil throughout the engine, ensuring the crankshaft operates smoothly and is properly lubricated during its operation. Before the crankshaft is deemed ready for shipment, it undergoes thorough non-destructive testing, NDT, which includes techniques like magnetic particle testing, MP, to detect any surface or subsurface defects that could compromise the integrity of the crankshaft. NDT ensures that no cracks, voids, or other flaws are present that could lead to failure under operational stress. This step is critical for verifying the safety and reliability of the crankshaft without causing any damage to the component. Once all the manufacturing and testing processes have been completed, the crankshaft is carefully packaged for delivery. The packaging ensures that the crankshaft is protected during transportation, preventing any damage that could occur during handling. The packaging is designed to maintain the crankshaft's integrity, ensuring it arrives at its final destination ready for installation in its intended application. Each of these steps is performed with the utmost attention to detail, ensuring that von Scheuwen crankshafts are produced to the highest standards of quality. The entire manufacturing process is designed to optimize the mechanical properties of the crankshaft, making it a vital and reliable component in any engine it powers, whether in automotive, industrial, or heavy-duty applications. At the crankshaft manufacturing plant, the process of forging involves a highly automated system where steel billets are fed into large-scale hydraulic presses with the help of robotic arms. This advanced system increases precision and efficiency in crankshaft production. The process starts with the robotic arms picking up heated steel billets, usually at high temperatures around 1000 degrees Celsius to 1200 degrees Celsius, red hot, from a furnace. These robots are highly accurate and are programmed to handle the heavy and hot billets with precision. This step ensures that the billets are fed into the press efficiently and with minimal risk of contamination or damage. Forging in the 12,000-ton press. Once the steel billets are in position, they are placed into the 12,000-ton hydraulic press, one of the most critical components in the forging process. The press applies immense pressure to shape the billets into the rough form of a crankshaft. The immense force, often exceeding 12,000 tons, molds the steel under controlled conditions to form the crankshaft's main journals, counterweights, and throws. The press also trims away excess material, cutting off any unneeded portions of the billet to ensure only the necessary steel remains for the crankshaft. This part of the process is essential for achieving the desired geometry and size of the crankshaft. As the press completes the initial forming, the press also trims off any excess material, flash, that can be further processed. The trimming ensures that the crankshaft is made to precise dimensions and reduces the amount of post-forging machining required. This automatic trimming process makes the forging more cost-effective and time-efficient. After the crankshaft has been shaped in the press, the part still requires several additional steps before it becomes the final product. These include heat treatment, such as quenching and tempering, to enhance material hardness and toughness, followed by fine machining processes, such as turning, grinding, and balancing, to achieve the final specifications. This highly automated, robotic-assisted forging process results in high-precision crankshafts capable of meeting the demanding performance standards required in automotive, industrial, and aerospace applications. The integration of robotics allows for faster production times and more consistent quality compared to traditional methods, ensuring that each crankshaft is built to withstand the mechanical stresses encountered during engine operation. At the forging workshop, the process of transforming a steel billet weighing tens of tons into a precise, high-quality forged part is an intricate procedure that involves the use of heavy machinery and close coordination between skilled workers. These workshops often deal with large-scale components such as automotive crankshafts, industrial gears, or aerospace parts, where precision and material strength are paramount. The following outlines the steps involved in the process, highlighting the advanced equipment and teamwork required to complete the task. The forging process begins with the heating of a steel billet to a high temperature, typically between 1000 degrees Celsius and 1200 degrees Celsius. This is done in a furnace specifically designed for high-capacity heat treatment. The heat makes the steel more malleable, allowing it to be shaped without cracking or breaking. At this stage, the steel is red hot, and its physical properties are altered to make it suitable for further processing. Once heated, the billet is moved carefully to the forging area. Due to the high weight of the billet, it is often handled by large machines or robotic arms, ensuring that it is securely moved to the next phase of the process without risk of damage or contamination. At this stage, the billets are picked up and placed into position by robotic arms. These robots are not only used for handling but also for ensuring the correct placement of the billet into the press. The steel billets, now glowing red hot, can weigh tens of tons, and handling them requires precise movements to ensure they are aligned perfectly within the press. The workshop will often employ 2 or more robotic arms that work in unison. One arm is responsible for lifting and positioning the billet, while the other may help adjust the angle or orientation to ensure the billet is aligned properly. The workers in charge of these robotic arms monitor and control their movements through highly advanced control systems. They ensure that the billet is carefully and precisely aligned in the hydraulic press, as even small misalignments could lead to defects in the final product. This level of precision is essential because any error in alignment could result in an uneven distribution of pressure or an improperly formed part, which would fail to meet the rigorous quality standards demanded by industries such as automotive and aerospace. Once the billet is securely positioned, the massive hydraulic press, which can exert thousands of tons of force, begins its work. The press shapes the billet by applying extreme pressure to form the steel into the rough shape of the final product. This high-pressure forging process is essential for altering the microstructure of the steel, improving its mechanical properties, and reducing any potential weaknesses in the material. During this process, excess material, referred to as flash, is squeezed out from the billet. The flash is typically trimmed away, as it is not part of the final forged piece. The removal of flash not only ensures the correct size and shape of the forged part but also minimizes the amount of material that needs to be discarded or reprocessed. This helps reduce waste and makes the process more efficient. In a forging operation involving such large and heavy billets, precision in positioning is critical. Even after the billet is placed into the press, slight adjustments may be needed to ensure the material is being forged symmetrically and evenly. The workers and robotic arms work together to make real-time adjustments as necessary, repositioning the billet to ensure optimal shaping. The robotic arms are highly responsive and can make these fine adjustments swiftly and accurately. In some cases, additional equipment such as alignment sensors and automated positioning systems is used to ensure that the billet is placed with the highest level of accuracy. This collaboration between human operators and automated machinery is what ensures that the final forged part meets the precise specifications required. After the initial forging, the shaped steel part is still not ready for final use. The forging process leaves the material in a rough form, requiring several additional steps to refine it. These steps may include machining processes such as turning, grinding, and polishing to achieve the final dimensions and surface finish. In addition to these, heat treatments such as quenching and tempering may be applied to the forged part to increase its hardness, tensile strength, and resistance to wear and fatigue. These processes are essential for preparing the part to withstand the high stresses it will encounter in its operational environment. The forging process in these workshops is a highly coordinated effort that combines the expertise of skilled workers and advanced robotic technology. By using precise, automated systems to handle the billets, position them accurately, and apply immense pressure to shape the steel, the process ensures that large, complex components are forged with exceptional accuracy and strength. This combination of human expertise and cutting-edge technology not only improves efficiency but also ensures the production of high-quality, durable forged parts used in a wide range of demanding applications.